When we've looked at quantities like position, velocity, and acceleration, we've already mentioned that these quantities are what we call vectors. Now, these are numbers that also have associated with them a direction. To go forward, we're going to need to know a little bit more about how to do math with these quantities. So in the first of these videos, we're going to take a look at how to treat vectors graphically and do arithmetic manipulations with them graphically. In the next video, we'll take a look at them using components and learn how to do those same operations using components. And it's been shown by mathematicians that these two approaches are equivalent. So normally when we represent a vector graphically, we draw an arrow. Let's just say this is a displacement. We'll call it A for now. When you write a vector, when you write a letter that represents a vector, you usually put this little funky half arrow thingy over it, and that's just to represent that this quantity A is a vector quantity and not a scalar quantity. A scalar is just a fancy way of saying just a number. We'll represent the numeric part of this by its length. So the length here we usually call it as the magnitude of the vector. And if I were to refer to just the magnitude of this vector A, I would write A without the little half arrow thingy over it. And by the way, if you look in especially older textbooks, instead of having the little half arrow thingy over it, you will sometimes see them instead set the vector in boldface and the magnitude in italic. But when you're writing by hand, since you can't really write bold or italic by hand, this is how we do it. All right, now let's say that we have a second displacement. We'll just go ahead and call that B for now, like so. So what this would be here is I'd say, okay, I'm going to the right, and then I'm going up, or I'm going east, and then I'm going north. How could I combine these two displacements to get the total displacement? Well, it turns out that there are two mathematically equivalent approaches, and I'll show them both because in my experience, at least I use each of them about half the time, depending on what's more convenient for the problem. But if you really gravitate specifically to one or the other, that's fine. So the first way that I'm going to show you how to add these two vectors together to get the total displacement is what's called the tail to head rule. And it's just what the name suggests. What you do is you put a copy of that vector, of the first vector, say here, and then another copy, and a copy of the other vector. You will move so that its tail touches the head of the first, like so. So this is my vector A, and that's my vector B, like that. So I put the tail B to the head of A. Because vector addition does commute, I could have done it in the other order, but this is how I'm doing it. And then to find the vector sum, what you do is you connect a new vector from the unconnected tail to the unconnected head, like so. And we usually call that the resultant vector. So my net displacement is, remember, displacement doesn't care about path. So we don't care that I went first here and then here. My total displacement is going to be this distance in this direction. Now this thing where I made the copies, you'll notice that I kept them parallel here. The fancy term for this is you make a parallel transport of the vectors A and B. So you would imagine taking this vector and sliding it to where you needed to do it. You take this vector and slide it where you need to do it. So that's, you may hear me talk about making a parallel transport. That's what I mean by that. Let's go ahead and do another example just to show what happens if we don't have nice, clean up, down, right, left vectors. So let's do another displacement. Let's say C and I don't know, D, like that. All right, so I can play exactly the same game I played before. Copy, paste, move it. There we go. So got a fresh copy of C there. Copy, paste, a fresh copy of D. And again, I'm going to put the tail of D to the head of C. And then to get the resultant, I will go from the unconnected tail to the unconnected head. So when you add vectors, you put the tail of one vector onto the head of the other. And then you get the resultant by connecting a new vector, by drawing a new vector that goes from the unconnected tail to the unconnected head. So you use this tail to head kind of thought twice in the process. Once for the construction and once for finding the resultant. There is another method, and this has been shown to be mathematically equivalent, called the parallelogram rule. So in the parallelogram rule, instead of putting the vector's tail to head, what you do is you attach both tails to each other. So let me go ahead and once again, let's just do C and D here. Copy, paste, we'll put a fresh one here. Yeah, that's as good as anything. And D, copy, paste. So now I'm doing is I'm connecting the two tails to each other like that. Now, in the parallelogram rule, what you do is you say that my vectors C and D here, pardon me here. Let's do a better job of labeling. There, much better. So my vector C and D here, what I'm doing is I'm imagining that these are two sides of a parallelogram. And what I will do is I will imaginarily complete the other two sides of the parallelogram. So going from here, I will go out parallel to my vector C like that. And here I will go out parallel to my vector D like that. And then to get my resultant, I go from that same corner to the opposite corner that I identified by finishing off my parallelogram. And that is my resultant vector. And either of these approaches are perfectly valid. They will always give the same answer. The only thing where you need to use one specifically versus the other is, say, if you've got two vectors that are parallel or anti-parallel, you won't be able to use the parallelogram rule for that. You'll have to use the tail to head. But for anything else, either approach is fine, and you'll always get the same answer. And personally, I find that it's about a 50-50 split when I'm thinking about kinematics type stuff. I am more likely to use the tail to head rule, and when I do forces, as we'll see in a later video, when we start drawing free body diagrams, you tend to draw diagrams where the tails of all the vectors are in one spot. So then the parallelogram rule becomes maybe a bit more useful. Okay, so this isn't the only mathematical operation that I want to show. So let's talk about doing multiplication by a scalar. So I can take a vector and I can multiply it by just plain a scalar quantity. And to do, since remember a vector is a number with a direction, what I'm doing is I'm multiplying the number. So let's say this is my vector b. If I wanted to have a vector that was, if I wanted to have the vector 1.5b, all I would do is just draw a vector that points the same way, but is 1.5 times longer. That's it. And if I wanted to do 0.5b, I just draw one that's half the length like that. There we go. And if I wanted to negate, there what I do is I flip the vector. So if I keep its length, so I draw a vector the same length, but anti-parallel, which means to point in the exact opposite direction. So that's my vector negative b. I do this in order to introduce how to subtract two vectors graphically. And we've touched on this idea a little bit already, talking about displacements. There are two ways to do vector subtraction. However, I will not teach the head-to-head rule in this video. The reason for that is that I find that when I teach it, half the people who learn it get exactly right, and half of them get it exactly backwards. So following Nightingale's first rule of nursing, which is first do no harm, I'm going to show the one way that I know seems to be pretty bulletproof, which is just to add the negative. With time and practice, you'll be able to intuit the head-to-head rule for yourself. So that's exactly what I'm going to do, is we're going to go ahead and add the negative. So let's say this is my vector A here, like so. And oops, this is my vector B, let's say, like so. And what I'm interested in is finding out what A minus B is. Let's say these are two positions, and I want to get the displacement, for instance. So the idea is we can say A minus B is just like we would be doing if these were scalar quantities. We can say that's the same difference as A plus negative B, like that. And then we can go ahead and add these two either by the tail-to-head method or by the parallelogram method. Either way works. But however you do it, the first thing you have to do is, so I'll do it by parallelogram here. So you would make another vector A, like so. But now I'm going to add to it a vector negative B. So that's just a vector same length as B. Whoops, I made my A too long. Let's try that again. About like that, right? There we go, something like that. So now I'm adding to it those negative B. So I've made a vector same length as B, but points in the exact opposite direction. And do make sure to label this as negative B, because that's what this is, because after all, in this method, you're adding them. And then I can go ahead, complete out the parallelogram. Oops. Like so. We'll have to imagine that that was a parallel line. Let's try that one more time. Okay, that's a little better anyway. And then we can That's so awful, I can't stand it, sorry. There. That's better. And so anyway, I'm connecting via the parallelogram method there. There's my resultant vector r, which that is equal to a plus negative b, which is the same difference as subtracting the vectors a and b, like that. Alrighty. So in the next video, we'll introduce unit vectors and use that to segue into doing component treatment. Catch you over there.